Good evening, guys. Welcome to the Bay Area Apache Spark meetup. Delighted to see all of you here. I see some familiar faces. I've seen you before, either in Palo Alto or in San Francisco. We normally hold these meetups both here in San Francisco as well as in Palo Alto, so that way we actually get the audience from a growing community around the Bay Area. So it's delighted to see so many of you here. If you do want to speak at our meetup, if you do want to sponsor us, if you do want to host a meetup, please come and talk to me. Or if you want to hear about a particular subject, dying to hear about it, please do let us know. A couple of announcements I do want to make before I actually thank and introduce our sponsors. Our second Bay Area meetup is going to be held in Palo Alto with Salesforce on May the 16th. The page is up. Please do RSVP because we do tend to fill up the area quite a bit. So make sure that you actually do that. We also have a Spark Summit coming up in June. How many of you have been to Spark Summit before? If you want a t-shirt, you might want to raise your hand. How many of you have been to Spark Summit? Brilliant, yeah. So we do have, coming up on June the 15th, there's a 15% discount code. Just use Bay Area MU, which is members for this group. So this is our 10th Spark Summit in Moscone, and it's going to be huge. So we're looking forward to see some of you today. That's about it. I'm from Databricks, and we are doing a lot of exciting stuff. Spark is not the only thing we do a lot of stuff with the cloud. So if you're interested to work, we are hiring, talk to me. Good challenges, and meetups are normally a good place to recruit, so might as well. Now, today I really want to acknowledge and thank Grammarly, who are our sponsors. Give a big hand to Grammarly, who actually are sponsoring this and all the spread that you actually have. In particular, I want to call out a couple of names. Tiffany, who's actually sitting up in the front, has been very instrumental in coordinating everything, so I really want to acknowledge that. And then Kevin is here. Kevin from Adobe gave us this beautiful place to host this meetup, so give him a big hand. And our first presentation is going to be from Grammarly. Now, people haven't heard about Grammarly, and I think about Grammarly as, I got some propositional phrase that I want to make sure that I don't have a dangling modifier or my subject and verb is somehow, both in tone and subject and in number agreement. But there's a lot of exciting things with Grammarly actually does.
Again, the topic of today's talk is it a good idea to use Apache Spark as a platform for powerful custom analytics that you build internally? And first few words in addition to what Pramod just said about myself. So I have been working at Grammarly for about 3 years now. Before that, I worked at Amazon. For the last 5 years, I've been mostly focused on building analytics pipelines in the companies, and even like on the bigger scale, I'm mostly a JVM engineer, and for the last 3 years, I've been a big fan of Scala and Spark. So I love what I do right now. And today, as we talk about analytics, first I wanted to just talk a little bit about what analytics is in a consumer product company, just to get us all on the same page. And essentially, it's a tool that helps better understand, I have this one, who are our users, how do they interact with the product, and some other details like did they get in, how much did they engage, when do they pay, why do they leave, and so on. And so essentially, it's crucial for the company to make our decisions data-driven, and almost everyone in the company would want to use it, like from product managers to marketing team members to engineers to support. So you can think of something like this. So you need to feed it some data, and it should provide insights about almost everything users do within the product to make decisions data-driven. I'll start with the right side of this chart, which is some few examples of reports you usually want to do. One of the super simple and obvious ones, let's say we want to plot number of unique users per day. Quick note, this is dummy data, it doesn't represent anything real at Grammarly. The other kind of report, which is slightly more difficult, slightly more complex, is retention analysis, which is basically a report that lets you understand for a certain cohort of users, say that registered during a certain week, how many of them are still there using Grammarly on week 1, week 2, and so on. One other important crucial report is funnel analysis. Say users come in to the product, laying on some landing page, welcome page, and proceed to create an account, and then finally install a product. And we want to see how many of them churn after a certain step, and like eventually maybe optimize it, set up some A/B testing, and compare those two groups using this metric, using this report. And the fourth example we'll really go back to multiple times today is the following one. Say we want to plot amount of conversions to pairs, so basically how many users bought the subscription per day, and want to split it by the traffic source that this user originally came from.
So simple but complicated question. How much does performance matter?
It matters quite a lot. Basically, the faster you make analytics work, the faster users can drill down even deeper into your data, and this would encourage them to better understand your users. So it's quite important. So now let's understand for this particular report, what kind of data would we need? And we essentially would need two bits of data. First is the landing page visits, which essentially hold the information about the traffic source user came from, and then subscription purchases. So it turns out that almost all that's happening within the application could be kind of abstracted to so-called events, and that's what we do, and many other analytics products out there would do similar thing. We can represent it, say, as a JSON, which would have like event name, property, which would specify the kind of event and some specific information for each event that is relevant. And turns out that for this particular report, we will not plot the second one, but we want to slice it by the data available in the first one. So inevitably, we would either need to enrich the data, which is like add the dimension to subscribe event, which is going to be like traffic source, or join these events. In many cases, turns out that joining during the report time is kind of too slow, or even impossible to be delivered fast. So it makes sense to pre-aggregate or pre-enrich the data. So we could, after we kind of figured out what requirements we would need to run these simple examples, we could visualize the analytics pipeline like this. So we want to capture data somehow, and to maybe enrich or pre-aggregate it, then put it to some storage that allows on-demand querying, and then some tooling that actually allows to build those reports, this querying. So it turns out that using some third-party tool that would do that doesn't scale for a long time. Eventually, you end up having too many constraints that require you to hack things around, and it dramatically decreases your ability to trust the data and achieve enough quality. And as you grow, like the smallest deviation from truth becomes more and more expensive. So why wouldn't we build this thing? And I'll start with the first part of it on the left, which is how do we capture? And it's kind of essentially not that complex thing. So we just have events happening throughout the system, and we need to collect them somehow. And this thing that would collect them would need to satisfy the following requirements. It should be always up and resilient in case, like some client send another event. We should try hard to capture and write it down. Otherwise, we lose it forever, most likely. We should be able to kind of handle spikes or provide back pressure ability. It's typical that, like, at some point of time, your product uses spikes, and we don't want to lose data as well. And hopefully, this thing would be able to buffer data in case the rest of the pipeline is down, or we do some maintenance there. We'll be able to get back and process this data. So what we did was we simply built a simple REST service that's doing nothing but on top of Play. That's doing nothing but putting data to Kafka. And Kafka is a great tool for that. It satisfies all these requirements. Distributed, scalable, buffers data, like holds data for some time and allows to get back to it. And we can even like connect to put data directly into Kafka for, say, some servers to server tracking. And so probably the next step you would want to do is put this data to some long-term storage. That's what we do. And in our case, we chose obviously Spark for that. It's great because it already has connectors to all of these databases you would want to use. And we put data to to Cassandra table. And it's literally 2 lines to implement that. And we do it in a microbatch fashion, not using Spark streaming yet. So that's what we do. The second step you would want to, yep, sure. Why RDDs, not data frames? Yeah, essentially, RDDs are great when you need structured kind of data manipulation, when you really care about those dimensions you would have with data. And at the point when data is being ingested, we're actually not very sure about the structure of those events. We might have like a big variety of different event types with different dimensions, and we just don't want to care about it that much. So kind of all the benefits of data frames at that point are not really relevant. Awesome. So let's proceed to the second part, which is much more hard and interesting. It's where we enrich and pre-aggregate data. And I'll go over the 2 types of pre-aggregation or enrichment we do. And first one is what we call user attribution. So going back to our 2 events, turns out that they are actually happening at the different kind of states of user. So when you land up on the welcome page, you are likely not authenticated. We know nothing about you. And then when you subscribe, you already have an account usually. And we actually want to work with your data like connected. So we actually want to understand that this page visit that you did while not authenticated is actually same you as did subscribe. So we would eventually have those events, both events have the same property fingerprint value, which is essentially, say, if it's a web-based platform cookie that lives for a long time on your browser. And what we want to do during this stage is just to append those user ID that we think this unauthenticated event belongs to with the attributed user ID property, which will have the authenticated user ID value on it. So how would we do that? If it's like a simple use case and there was just some user using Grammarly on a single browser, we would probably like just go over non-authenticated events until we see the first authenticated one, take user ID from there, and then write it down to all the rest of the events on the device. Obviously, there are some more complicated cases when you say you share your laptop with someone else and you both log in from time to time. But we could come up with some heuristics that will allow us to split those events between those 2 authenticated users. And if we talk about how we would actually implement in code with Spark APIs, we could think of something like this. So let's say we have RDDs with our events, and they are already sorted and partitioned by device or like fingerprint. And what we would probably do is like have some buffer for each partition where we would put all the events until we see the first one with the user ID. That's what we do in those lines. And then just take all that buffer contents with non-authenticated events, add the user ID to them, and output together. So obviously I'm covering the very simple case here with just one user and device. And the problem here is with this buffer, which potentially for outliers can grow very big and not fit memory. So how can we handle that? We can actually kind of face this problem ourselves and start solving it. So let's first figure out how Spark dealing with memory on the worker nodes. And the idea is very simple. So your whole memory is split into 2 parts. One, bigger one by default, which is 75%, belongs to Spark internal needs, and usually for either shuffle operations or caching. The rest of it, which is usually 25%, belongs to your, you're allowed to use this memory. So you kind of end up having, you're being very constrained. So isn't it a good idea to try getting into this blue area and actually also try to be as safe as Spark, because like obviously Spark, even with this default configs, doesn't fail with out of memory when you shuffle, say, sort more data than fits into the node's memory. So how would we do similar things? And the idea behind how Spark does it, say, for shuffle, is pretty simple. Say, like in case of shuffle, you need some kind of in-memory array which will, say, sort if it's a sort shuffle kind, and the way how they would implement such collection, managed collection that would always definitely fit into memory is the following. So the code would do the following logic. We would ask for Spark memory manager. There is such an entity for a certain amount of memory. Say we are granted it, and we start pouring data into this collection, in-memory collection. Once we hit the limit we were given, we will request more, actually twice as much, and keep pouring data in. And once we hit the limit once again, say we ask memory manager for more memory, and it turns out it's already occupied by other tasks running the same worker. So what we would do is we would spill the data to disk and release memory, and continue the process until we have, say, a certain amount of data memory and several, say, files or blocks of data on disk. And then your collection would have to be able to process these several blocks of data on disk and what is in memory to reconstruct the collection you need. And that's what we basically want to do. Say we would want to implement spillable buffer that would use this mechanics and Spark APIs to achieve this. So to implement it, you would need to work with the following APIs or entities that Spark exposes. First one is task memory manager, that is actually allowing to kind of request or like occupy certain amounts of memory on the node, so you can acquire and release. And then you would probably want to extend the spillable collection that is actually implementing all the logic around requesting more memory from Spark Memory Manager, twice doubling the amount of memory you have. And you would just have to implement the spill method that is going to write data to disk otherwise. And one other great utility Spark already has is a size tracker trait, which you will use to wrap your in-memory collection to estimate its size. So this thing basically can give you an approximate amount of memory your in-memory collection occupies, and it's doing it efficiently, so you can do it like literally on every append to collection, and it's doing it by collecting samples every now and then extrapolating when you actually request the estimate. So using all that, you could actually go ahead and implement collection and benefit all these cool things, cool results. First, you would get outside this limited amount of memory you are kind of given by Spark by default, and be safe with the situations when you don't fit even that amount of memory. And Spark APIs are already available to make your life easier implementing this logic. Maybe they could be a little bit more friendly, or at least more documented for like wider adoption. I haven't seen many examples of people using it, so like just reading the source was my kind of inspiration in this case. Right, so in our example, we would just replace this buffer, which was like a simple array buffer, with this new spillable buffer we will implement using all this code developed in Spark, and it will be stable even for outliers with a lot of data that we would want to cache. Right, so let's go to the next kind of enrichment we do in our analytics pipeline, and what we call it calculable properties enrichment. And The idea, the example would be the same. So we have those two events, page visits that has information about traffic source and subscriptions. And what we want to do is we kind of want to add the dimension of traffic source kind to the subscribe events. And we basically want to take it from some other events that user had prior to the subscribe events. And what we basically did is wrote a bunch of code, which is essentially exposing Scala-based functional DSL, which allows you to, in a pretty expressive and compact way, express what kind of transformation, like what kind of reduce operation you want to apply on users' events up to a certain point to enrich a dimension to event. And as a result, we tried to achieve the following requirements when we were implementing this: benefit from kind of all cool side effects of functional programming, type safety, what Scala is famous for, making this very concise, composable, and reusable, and testable. Yeah, and it's kind of pretty similar to existing Scala collection APIs, but like very different in terms of how it works under the hood. And we support batch and streaming modes there, so we can, in theory, not theory, practically, we have done multiple times. We could change our mind about how we enrich data and recompute it for all the historical data that we have. And we also support streaming mode, which is efficient in terms of that we don't have to, reduce the whole user timeline, the whole set of user events to enrich the next event that just came in. So we can do it incrementally. Awesome. So this was what kind of enrichment we do with our data. And now let's maybe cover a bit how we actually implement in terms of Spark jobs, those two kinds of pre-aggregation we do with our data. So as you remember, we have this pretty simple setup where we just took data from our incoming Kafka topic and put it to some permanent storage using some streaming bit of code. And to do the next step of data transformation, we would just have one more Kafka that this first streaming bit of code will also write to. And the next streaming bit that will actually perform the next step of data transformation, which will, again, write data to some permanent store and send data to the next Kafka, after which the next stage of enrichment, which is in this case scalable properties enrichment, will live. And the final data store is our so-called index, which is a data store that is supporting querying on top of it. And because we mentioned we want to change our mind about how we enrich data for all the historical data we have collected, we would probably need a batch mode. So kind of seen a Lambda architecture set up here. And yeah, we use Spark everywhere on this picture. It's great for all this because it has connectors for everything already. So it's pretty easy to swap different storages and just write data to one more of them. It's great for batch mode because it's supporting shuffle with spilling, which is basically can operate with the data that doesn't fit memory, and if it fits or while it fits, it's very fast. And it has failure recovery built in. And when you have a very long job, like what you don't want to have most is your job like failing somewhere in the middle after 20 hours waiting with some error that could be retried. And it's great for streaming for two reasons. It's very fast. It has low overhead. Basically, you can run your jobs every 5 seconds, and most of the CPU will be spent doing your actual work. So let's take a deeper look into one part of this diagram, which is, say, a single, in this case, microbatch job that has to take data from one source and write it to many destinations. So how would we actually implement it using Spark code? Let's do the first try. Say we have RDD with data, or data frame, doesn't really matter here. And we would use the connector to Kafka in this case to write it to Kafka topic, use the connector to Cassandra to write it to Cassandra table, and say we want to write it to one more Cassandra table like some part of this data, say. So if you actually run this code, it will turn out that each call to, like, say, save to Cassandra API would actually trigger the RDD for each partition built-in method, which will actually trigger the run job on Spark context, which will actually launch the job, basically read the data, apply all the transformations you had with the RDD, and then save it to your destination. And you will end up, instead of having a single job that writes to multiple destinations, 3 different jobs, each of which reads the data from Kafka, in this case, and transform it in the way you want, and write it to a destination. And it can be like not what we want, because say maybe for streaming it's okay, but for batch where it takes just a long time to read the data, you wouldn't want to wait 3 times for or however many times you need to write data to some destination till it's all done. So let's try again. Maybe we would use the cache API that Spark has to actually save the results of the kind of reading and transformation and just try them 3 times to these different destinations. That would help, but not completely, because actually we'll still have 3 jobs, but the second and the third one will actually read data from cache instead of reading from Kafka, which is probably okay again in streaming mode, but in batch mode this will not fit in memory likely, or you would then have to switch to disk on cache, to cache on disk, and it's like probably not going to be worth it at all. Probably Kafka is not that slow compared to on disk cache. So how would we overcome this? Let's dive deeper into how a single, like this, write API implement in typical connectors. So they would likely have something like a writer. In this case, we'll do a simple version of it, which is going to just write data to file. So we would create this standard Java API buffered writer over output stream writer and so on. And we'll just take the iterator in each partition and write all elements to this file and finally close the writer. So very simple and convenient. So important note here is that each writer that we would use, like in this case, simple file writer, but say for Cassandra connector, should really care about those things. Each writer should be buffering the data so that we not block our processing, because this iterator can actually cause some CPU intensive work to be happening. So we don't want to block on every time we process an element to try get the maximum utilization of our CPU, let's say. And we want to care about idempotency here, because, like, as I mentioned, Spark will retry your job, your task if it failed. We don't want to end up having duplicates in the data, or our store or the next steps of processing should be fine with duplicates. So why won't we try to fix this and change it to something that will support multiple destinations writing for a single task? So let's, instead of for each partition, use map partitions, which is not triggering any kind of job launch right away. And instead of doing for each iterator, we'll do map and write each element there. And they actually use some magic to close the iterator, close the writer once iterator is exhausted. Yeah, that's actually what we did. We implemented for each of the each of the connectors we use, like Cassandra, Kafka, Hadoop, and it allows us to actually kind of launch these intensive big batch jobs, which are able to, in a single, during the single processing of the data, write bits of it to multiple destinations. So yeah, that's the thing. I would hope others could benefit in their scenarios, especially for the batch processing. The only important thing that you should care about is each of these writers that you would stack up for the task will occupy its own resources. These buffers I mentioned, or I/O resources like open files or network connections, and you should be mindful about that. So have enough memory, or just don't get crazy about how many destinations you write to simultaneously. All right, just a little bit of stats about our pipeline. So we kind of have order of magnitude of 1,000 events per second at the moment. It actually kind of drastically changed over the last 2 years as we got much more users and much bigger coverage of the product. So far we have accumulated terabytes of compressed data, probably compared to the scale of huge companies like Google, it's not that much, but we expect to grow further and try to think about it moving on, what if we had 10x data, 100x data. So now let's quickly talk about how we store data which we would want to query. We do a lot of things there, actually. I will not probably have time to talk through all of them in this presentation. Feel free to reach me after the talk. But few important and interesting things that you would really want to use columnar data storage for that. In our case, we don't use high-level products like Redshift or Google Bigtable. We rely on Parquet, manually store files on S3, manage how we partition data into, say, these files, Parquet files, by event name, basically by our user scenario, which is likely separate files for different events, and group data by time interval. Because your columnar data storage is not playing very well with changes, say, if you want to update certain event and we need to do it, say, for this user attribution needs, we apply the same tactics storages like Cassandra do, which is write changes next to existing data and merge on the fly when we query, and have some asynchronous compaction process. We care about how we actually communicate with data over S3. It has some interesting optimization points, like how would you name those files to achieve maximum parallelism, or how would you guarantee read after write for your data. All interesting aspects. We'll be happy to chat about this. One other thing which excites me most, and I was hard enough to tell about this last part in this last part of the presentation, which is how we query data. So first mode of query, like billing reports, which you're probably all familiar with, is kind of this hardcore kind of mode where you would just use programming language to express your reports. Spark has a great data frames API, and this is a great use case for this kind of scenario. We kind of, after we process data in our pipeline, we end up having this Parquet files with structured data, and benefit a lot from this data frames API. We use Zeppelin as a UI to build those ad hoc reports at scale. And this has been fantastic. Usually you have felt the same when switching, say, from pure SQL to either pandas data frames or our data frames. It's much more convenient to express yourself in this combination of SQL and actual programming languages like Scala or Python is. But the more interesting and challenging aspect, how would you enable everyone in the company to build reports, people that are not going to learn programming language, or it's just not worth it to express yourself like in SQL or instead of Scala commands like lines of code. So let's consider an example. So we want to plot unique visitors daily. We want to apply some filtering, say by country. We want to split the chart into multiple ones by traffic source users came from, and we only want to show it for the top 20 because there are a lot. We want to constrain the time range we look at. And it's a pretty simple query you could think of. And eventually, once you add up features like slightly more over this, you end up having a very complex either SQL or, like in this case, Spark SQL DSL code. Actually, you have much more complex reports than those I mentioned. So another approach could be like, hey, what about building some UI that would allow you to express yourself with a kind of, these drop-downs, forms, and different controls that would allow you to let whatever code you wrote understand what kind of report you would want to build. And turns out it's very expensive to build such UI, expensive to extend it and support it. Like this thing could become bigger than all of your Spark code that you would have. And we tried to kind of combine the ease of use of tailored user interface you would have for a particular report with the idea of expressiveness of your code, say in SQL, and came up with a custom query language, which is tailored to a particular set of reports teams would run, and borrows a lot from SQL for those who are familiar with it. In this case, all the expressions in this query, say within where statement, which is like very similar to SQL where statement, are actually completely borrowed from SQL language. And how would we actually do it? And how, like basically probably implementing language is hard and expensive. And turns out with Spark it's completely not. So Spark already has a SQL parser that can run normal SQL over your data in data frames. And they would have a class hierarchy which starts with expression class, which is the class that allows you to turn your row of data into a value, right? So that's the essential thing you need for these expressions, say your where filter in SQL query, and say to implement a mathematical like algebraic add operation, you would put something like this into your eval method, which is basically take left argument, take right argument, compute them, and sum them up. And there is actually code there in Spark code base that's implementing a parser for this add operation expression. And it's done using Scala parser combinators library, which is a fancy way to express your, to build your parser for any kind of language. And it's very concise and eventually easy to understand. This kind of crazy symbols that you would have in typical Scala DSL, but eventually it's very, very concise compared to, say, NTLR library. And we kind of just moved on. Took the existing expressions parser that they have in Spark SQL, extended with our custom structure for these typical reports, and built the parser for each of the query types we would have. In our case, we have segment query report, segmentation, funnel analysis, and retention. And we can easily build much more. Just let us know what kind of typical reporting you do, and we will add it. Turned out to be a great idea. We have built out all of it pretty fast. Like one downside or like bad news is that in Spark 2.0 they shifted away towards an NTLR parser, and do not longer have kind of this expression parser built in, but actually I can just borrow it from the previous version. Kind of the expression hierarchy didn't change, it will work completely fine. Maybe I would expect this part to be like slightly more extensible. Maybe we could just share with Spark community and Databricks that it's really a cool thing about Spark being able to write your own query language. And yeah, I would encourage everyone to try it out. And I wanted to show a quick demo how the querying experience looks currently at Grammarly. And yeah, you just end up writing some bits of text. And the cool thing is that when you have your own parser, you can do a lot of magic around it. So in our case, let's write some segment query. You see, it changed color, so we actually went ahead and used the same parser to color code, like to add syntax highlighting to our query. And then say we would want to query a particular event. In this case, say it's going to be like some funnel payment form event, and boom, we can have autocomplete, and it will actually be kind of taking into account where in the query you are typing, so what kind of data to autocomplete. In this case, only event names will end up being here. We have this nice kind of familiar to engineers editing experience where you can look up for things. Yeah, as you probably observed, we would even have documentation pulled up from the specs we have for our tracking. So there we hope that it will really make easy data exploration and allow everyone in the company to just go ahead and check out what kind of data we have, how we can slice it, by which dimensions are available there, what kind of tooling you have to transform the data, like functions, like they have in SQL. We will also support them here same way, and so on. So like, yeah, you would probably go and write time constraints in the form like this, say from 2 weeks ago to today. And isn't it great to express, your time range in this nice form compared to like this date criteria in SQL. So yeah, that I unfortunately I won't be able to run the query and show you the data for privacy reasons, but that's what we do. And a few words to conclude. Sorry. So turned out building your custom analytics pipeline after you probably grew to a certain size makes a lot of sense, doable and enjoyable, especially on top of Spark, which has an amazing amount of extension points. It has great source code, so you can just go ahead, drill down, understand how it works, and extend it in certain places. It's great for everything you would need in analytics, like data processing in batch and streaming mode and querying, so it's like universal. And yeah, it would be great to see like deeper and deeper tweaks and integrations into Spark, more accessible, like for developers, not just this high-level developers API. Would be great to discuss it with the community and those who build Spark in Databricks. And we are hiring, of course. We have a lot of positions in every team. We can basically, almost any kind of specialist can find a job at Grammarly. Feel free to get in touch with my team members who could tell more about Grammarly, look around, they can wave their hands and talk to you more about Grammarly. And I will be happy to answer any questions you might have.
Thank you, guys. Give them a big hand to Mikhail. That was a really in-depth way from top level that Pramod talked about all the way to hands-on, how you actually change the rule writing DSL. So this is actually what happens when you make grammatical errors, when you're dangling modifiers out of place, or when you have a verb disagreement. This is the complexity that actually goes underlying it. We just got a few more minutes, so I'm gonna have to ask you to, we'll take 3 questions because we have another second speaker. We don't have a third speaker today because they couldn't come because of the traveling complications. So we'll take 3 questions. Misha is going to be here. Pramod is going to be here after the talk. There's lots of beer. There's lots of food. We'll have a good party after that. So let's try to keep it quick so we can actually get going. So anybody? Right here.
Hi. Hey. I have a question about data storage. So initially you mentioned Cassandra as your storage, and then you had S3 and HDFS in a couple of slides. So only HDFS allows you to collocate compute and storage, I think. Do you ever take advantage of that, of like running your Spark cluster on the same machines that you store your data? Or do you usually keep the data somewhere and load everything every time you want to run a compute operation?
Thank you for your question. So that's a great question. I love to think about it every day. The trick is that what you want to get to, like what's the most critical for your query is how fast you can answer with the results of your query, right? So for that you need 2 resources, CPU and the speed of, the disk resource, like basically how fast you can pull the data from whatever storage it is. And the great thing about the cloud and AWS S3 or like, it doesn't matter which kind of cloud you would use, but like this, for this file store solutions, that they have a great parallelism, and you kind of pay only for the usage. So basically, if you want to run a storing query, like very high stress test report, and get a lot of data out of it very fast, it's probably going to be more efficient to use the cloud instead of your own managed HDFS. So for that reasons, we prefer to benefit from the not have the collocation effect, but instead to have higher parallelism in terms of being able to pull data. Would be great to see Spark evolve at some point to have a similar kind of benefit for your CPU, which like say become something that runs on top of AWS Lambda or some other serverless infrastructure to also allow you pay just for amount of CPU cycles you used. Because in analytics, for the querying part, you definitely have kind of rare stress use case situation instead of continuous, predictable resource usage. Hope I answered.
Anybody else?
My question is, do you have a long-term catalog for all the tables or data frames you have in your storage?
Yeah, great question. So yeah, I didn't mention that, by the way, but basically, I will answer in 2 parts. First, as I said, everything with storage Grammarly analytics pipeline is an event, and kind of they are similar and like they are equal in terms of what they are. Either it's high volume text check event, or it's like a rare say jobs page visit event compared to each other. So they live in the same set of tables and storages. So that's the first aspect. Second one, yes, to store data like outside managed database, which AWS S3 is, you have to keep track of what files you have there, like in what directory structure, like prefix structure they live. And one option is to use something like some already designed setup, like what they have in Hive, for example, where like you partition data a certain way, or manage it yourself. So that's what we do. We basically have a SQL table that stores all the kind of file paths we would have and maps it to event names and time ranges. And we continuously update it as we process data and add it to our index.
Give it again to Misha again. Thanks a lot, guys. Thanks a lot.
Thank you.